Well, this talk is about domain modeling from functional to reactive. Before I start, just a quick show of hands of how many of you have been familiar with or have implemented domain models using some of the principles like domain driven design or similar things? Quite a few. And how many of you have used object oriented techniques in implementing those domain models? Functional techniques, purely functional techniques? A lot less. Okay. So, before I start, here is an important thing, an obligatory announcement. Use the GOTO mobile app to rate the session. That also is an important feedback to us, the speakers, about what we did well and what we did not. So, domain modeling. In this talk, I will be taking a somewhat orthogonal approach of object oriented modeling, and we will talk about functional domain modeling and try to make the model responsive, elastic, resilient, or if we combine all of them together, we call that reactive. What I will do is I will start with a basic skeleton of a functional model, and I will try to implement reactive principles on top of it, making the APIs reactive, mostly using algebraic techniques. But before that, how do we define a domain model? I actually like this definition a lot. It is from Wikipedia, and I like this definition a lot since it highlights the defining aspect of what a domain model is, that it is related to the problem domain. That is the defining part of a domain model. It is related to the problem domain and how the artifacts interact there to produce the correct domain behaviors. So, when we say that we are implementing a domain model, what we are doing is we are trying to replicate the behaviors of the problem domain into the solution space using some specific technologies. We will take a look at domain modeling through the functional lens. We will start with a basic functional model, pure functions, immutable data, and the algebra of types. In this talk, algebra will play a very important role, because algebra gives us the power to reason about our code, and that is one of the most important characteristics of a successful domain model implementation. A domain model has many constraints, the business rules, and using algebra, we can ensure that those rules are validated or verified. And then we will enrich our algebra to add some interesting effects. By effects, what we mean is some of the interesting things that traditionally can be handled. One example is exceptions. Traditionally, we use try catch handlers to handle exceptions. We will use effects to address failures here, because effect is an algebraic way of handling failures. And then we will see how to compose effectful functions to implement richer domain behaviors. So, ultimately what our domain model, a specific module or a specific function delivers, will be a cascading of effects. And we will make that reactive too by implementing reactive principles as yet another effect in the as part of the API. So, this is the primary agenda for today. We will formalize our domain model definition from the algebraic point of view, and this will lead us to the domain model algebra, which is a concept which is the binding contract that makes our model consistent and easier to reason about. We will start with a functional model and see how we can make APIs reactive using algebraic techniques. But as we will see that any complex domain model is not really one model, it is actually a collection of models, and algebraic unification breaks across these boundaries. We call them the bounded context. So, when we talk about beyond algebra, we will talk about bounded contexts and how algebraic definitions fail to unify across algebraic boundaries. For that, we will discuss how to design reactive protocols that unify across bounded context. Then we will take a look at actors and domain models and how we can use actors to the benefit of our domain model. And finally, we will conclude the talk with a discussion on reactive streams, which is a type safe and compositional way to implement workflows, stream based workflows in a domain model. Quite a few years back, Marius Ericsson of Twitter wrote this paper, Your Server as a Function. And what he highlighted in this paper is that it distilled, he identified 3 basic abstractions that happen to align beautifully with the style of functional programming. And these 3 abstractions were the distilling parts of all the servers that Twitter implemented. These 3 features are futures, services, and filters, which not only compose algebraically, but also gave them the proper substrate for building reactive servers. And if we think of domain models, a domain model is responsible for delivering a bunch of services. So, can we really think of our domain model as a function? Well, it may not be that simple, or a collection of functions. Some trivial models are, but as I was telling, that a complete domain model is actually much complex than that. This is how we represent a non-trivial domain model architecture, models within the main model, each with its own vocabulary and set of artifacts. Here we have a bunch of bounded contexts. You can think of bounded contexts as possibly independent applications, but they are not islands. They need to collaborate with each other as well. And as I was telling you, algebras don't unify them. The algebra can be defined within a bounded context. The algebra that we define is valid within the bounded context with respect to the specific vocabulary which that bounded context has with respect to the entities, the value objects, and services. For example, 2 bounded contexts can have the same entity, same name, same named entity, but with entirely different purpose. Suppose we are talking of a banking system. A banking system can have an entity named account, while we may have a separate bounded context which does authentication. It can also have an entity called account. Both are parts of the ubiquitous language, or both are parts of the vocabulary of that specific bounded context. But the account in banking context is completely different from account in the other context. Across bounded contexts, algebras break, and we need to define a more loosely defined protocol. We will discuss this when we talk about algebraic boundaries. As I said, a bounded context has a consistent vocabulary, a set of domain behaviors modeled as functions on domain objects implemented as types. The vocabulary is only valid within that specific bounded context. So, whenever we talk of any specific type or any specific entity or algebra, we are talking it with respect to a specific bounded context. So, keeping the earlier picture in mind, we can say that a domain model is a union of bounded contexts. And we can define a bounded context as a collection of functions subject to a set of predicates which we call the domain rules. So, fx is a domain function on an object of type x. In this talk, we will be talking about domain modeling with respect to a statically typed programming language, and I will mostly be using Scala for this. So, fx is a domain function on an object of type x that composes with other functions and closed under composition. What it means is that when I compose 2 functions, 2 domain behaviors, it gives me a bigger domain behavior. That is also part of this set. And all these functions will be applicable, all these types will be validated against a set of business rules. So, summarizing, what we have is, we have a collection of functions or morphisms, as we say in theory. We have types as sets, composition, and a set of rules and laws, and this forms our algebra. We have a domain model algebra, which is the algebra of types, functions, and laws. And one objective of implementing a domain model, one of the things that we would like to do is to make this algebra explicit. Making the algebra explicit will give us a lot of mileage when we have a decent type system at our disposal. Most part of the algebra will be verified by the type system. The compiler will be your friend. You don't need to write tests for validating those specific set of constraints or invariants. And we would like to have the algebra verifiable. Verifiable once again through type constraints. If we have a dependency type programming language, then we can have more constraints verified as part of the compilation time. And for those properties for which we cannot have compile time verification, we will have algebraic property based testing. So, making the algebra explicit and verifiable is what we should try to achieve when we think of a robust domain model design. So, summarizing once again, we have a set of domain behaviors, we have a set of domain types, we have a set of domain rules, and we will see this that we can express some part of our domain algebra in terms of already existing verified algebraic structures like monoids and monads, and there are a lot of others. And all of these form part of our domain algebra. So, now we refine our definition. We can say that the domain model is now a union of a collection of domain algebras, and the rest of the definitions stay the same. We define a domain algebra in terms of functions, types, and algebraic composition. Our algebra is valid within the bounded context. Algebra is the binding contract. We will make that reactive. We will see how to make the algebra reactive, or rather, we will try to make our effects reactive by expressing it in terms of existing algebra. And when we have multiple bounded contexts, each with its own algebra, we need something different to unify them, because algebras do not unify across bounded contexts. They are decoupled in space and time, as Jonas was mentioning. They have separate vocabulary. Every bounded context has a separate vocabulary. So, type based unification breaks down. We need to have protocols defined so as to establish collaboration between the bounded contexts, and these protocols need to be reactive. So, this brings us to this reactive manifesto, which underlies some of the core principles of what we mean by a reactive system. Being responsive is the ultimate goal, as indicated by that circle, and unbounded latency will kill your user experience, and 3 ways to achieve this goal are the 3 boxes indicated there, and we will discuss each of them separately as part of this talk. Now, let us start with a code fragment which defines some of the basic operations that we can do on a bank account. I am using Scala, as I mentioned. These are the related operations on a bank account that can be done, and we encapsulate all of them within a module. We make the module parameterized on types. This is one other important thing which we can use if we have a static type system at our disposal. We can design parametric abstractions, and this is possibly the most important part in this slide. The return type, note the algebra of the return type. It is a disjunction. I am using the disjunction operation from Scala Z, and what it does is it encapsulates failure as part of the algebra. So, we are not relying on any try catch block. We are not relying on throwing of exceptions from within our code. We are trying to incorporate that as part of the algebra itself. So, once again this shows that our algebra is explicit. We are explicitly coding the failure handling as part of the algebra. These are the operations which are terms derived from the domain vocabulary, domain behaviors, and the entire set consists of our explicit and verifiable algebra. It is parametric, statically typed, modular, and hence unit testable, and composable. In what sense it is composable? The algebra of the return type ensures that we can compose multiple operations into bigger domain behaviors. The algebra that we had here for the return type, that's actually a monad. Hence, we can compose smaller operations together to form larger operations. And modules in Scala can also be composed. So, we can form larger modules by composing smaller modules within our system. This is in fact a great way to evolve your domain model from smaller abstractions build upwards using algebraic techniques. But typically any operation on a domain model needs some database access. So, we need to have a repository. We need to use a repository from where to fetch data in order to perform any operations on the account opening or closing or anything like that. For any typical domain operation, any non-trivial domain model does that, and so we change the algebra of the return type to reflect that property. That we need to, the return type explicitly says that we need an account repository from where to fetch data, and that will result in the result type. So, an explicit change in the algebra. Sorry. Now, it so happens that the type that we discussed here, account repository to account OP account, this has a name. This type is isomorphic to what we call a Cleasley operator. A Cleasley is an abstraction, Cleasley is an algebra which gives us the ability to compose effectful functions, and this is an effectful function. Account repository to account OP is there, it is actually a disjunction. So, that is what we mean by an effect, and this is here the return type is an effectful function, and we enrich our algebra by encoding the return type as a Cleasley. So, we have more algebra, more functionality, more succinct. The advantage is that once we encode that as a Cleasley, we have all the combinators that Cleasley offers. Cleasley is an explicitly verified algebra. Cleasley has an Cleasley is an abstraction and is available as part of some libraries. So, once you can reuse that algebra, you get the laws, you get the constraints, you get the combinators for free. So, we enrich our algebra here by using the Cleasley. So, what it does is it enriches our algebra and helps us express our domain algebra in terms of an existing and verifiable algebra of a Cleasley arrow. But now that you have a database in place, your system is now more enterprise, and you need to ensure that the performance and response that your system delivers remain optimal even in the face of unpredictably large load. You can't have the user waiting at the user interface because your system has gone to some other continent's data center to fetch some data from a database. You need to bound that latency, maybe based on service level agreement or whatever. Unbounded latency is a killer. So, you need to bound that latency, and the way to do that is you cannot publish APIs that does blocking calls. Blocking calls will lead to unbounded latency, as Jonas was also mentioning in his talk. Blocking kills. So, we need to make our APIs elastic enough so that the perceived response to the user is not affected by the current load on the system. The user cannot wait indefinitely. Irrespective of how much load you have, the user experience should not suffer. That is one of the core principles of being reactive. So, now we are looking at this part of the graph, this part of the reactive graph. But we would like to do this without foregoing the benefits of algebraic reasoning with types. We would like to incorporate this reactive principle as part of the type system. Note we have a powerful type system. Why not use it if we can have it? So we would like to model this elasticity as much as possible using the type system, so that we can reason about the effect in a more sound and algebraic fashion. Note what we are trying to achieve is we are trying to achieve the effect of elasticity as yet another effect. Futures. Futures is the way to get there. A future is the essence of asynchronous non-blocking computation. Futures compose, they have an algebra, and they give us a great substrate to organize concurrent code in a compositional way without blocking the main thread of execution. So futures give us the way to make our APIs reactive without foregoing the benefits of algebraic composition. So in our use case, we would like to augment our domain algebra, the algebra which we left behind. We would like to augment it algebraically so that the API becomes reactive, and we will use future for that. Already you have seen a couple of effects. The effect of an either or disjunction. We had that as part of the algebra of the return type of the API. Cleasely, we encoded the return type using Cleasely in order to inject the database from outside, account repository. So we would like to have asynchrony as yet another stackable effect within our computation. Something like this. We have the core value, we have disjunction as an effect, we have Cleasely as yet another effect, and on top of that we would like to have future stacked as yet another effect, which will give us the way to make our APIs elastic. And the general technique we will use here for this stacking is by using the concept of monad transformers. Note we told that either is a monad. Cleasely also gives us composition over monadic functions. So we would like to use the technique of monad transformers to incorporate reactive APIs using algebraic techniques. How many of you are familiar with the concept of monad transformers? Okay, it's not essential to know details about monad transformers. The only thing is that here in this example, this is an example which does not use monad transformer. Here we are using two monads, the disjunction monad and the option monad. And note that if we need to get to the value A, we need to do two levels of peeling, two levels of for comprehension we need to do in order to reach the ultimate value to which we would like to have access to. Obviously, this doesn't scale. If we have lots of other monads, then there will be lots of for comprehensions. There will be lots of peeling needs to be done. Obviously, the code will not scale. On the other hand, if we use a monad transformer like option T, it actually what it does is it collapses the entire stack of monads into a single monad, so that you can use one level of peeling to get directly into the value. So here once again note that we are enriching the algebra of the type response by using a monad transformer, and richer algebra leads to less amount of client code. So monad transformer is yet another instance where powerful abstractions can lead to more succinct code base at the client level. So this is what monad transformer does, and this is our reactive API, reactive open. What it does is, note at the top the return type, either T future, it actually stacks future on top of the either data type, so that the return type is now a future. It's not an either anymore. So either T is the vehicle to get there. Either T actually allows us to stack a series of monads in order to get the required elastic behavior that we have been looking for. This is either T future, the type that I was talking about. And this is a breakdown. Previously we had a single monad. The disjunction, and now we have stacked it up with future using a monad transformer to make our algebra richer. And this is what I call reactive algebraically. So we have been able to achieve elasticity in our APIs without foregoing the benefits of algebraic composition. In fact, the implementation also doesn't change much. You only need to add these monad transformer at the top, and the normal logic remains as it was. So what we have achieved here is we have introduced the whole new effect of asynchrony to implement reactive traits in our domain model API, so that the user is not blocked. Instead of returning the result of the computation, it now returns a future, so that the main thread of execution is not blocked. And this is one example of how we can use, how we can gain from the benefits of having a static type system at our disposal. Future has an algebra, so the entire structure, entire return type can be verified algebraically. We are still in the statically typed land with asynchronous behaviors baked into our APIs. We can reason about our program statically. We can compose asynchronous components to form larger abstractions. And the composition part remains the same. Previously also we were able to compose like this. Now also we can compose our smaller operations to perform larger ones, despite the fact that we have enriched our algebra. So enriching the algebra in a type conformant way does not hamper composition, because the algebras align here. Compositional by types. Individual operations sequential, because it doesn't make sense to make each of them parallel, right? Open, credit, debit, each of them going parallel doesn't make sense. So the individual operations are sequential. But what we gain is the composed operation returns a future, and hence it doesn't block the main thread of execution. This is an interesting pattern in domain modeling, where despite the fact that all the operations return future, they have to be executed sequentially, but still the main thread of operation doesn't get blocked. We can have the other pattern as well, where we can have individual operations executed in parallel. For example, you are trying to compute the customer portfolio. In order to compute a customer portfolio, you need to get his portfolio for currency, for the equity, for fixed income, for all the types of instruments that he has. But all of them can be fetched parallelly. So here it's a scatter-gather kind of a design pattern. You scatter all the computations in separate futures as separate futures and gather them when they arrive. Something like this. So here I can start all of the operations in parallel and then finally compose them together here. The difference with the previous use case is that in the previous use case all the operations were strictly sequential. Here all the individual operations can be done parallelly. So this is one other pattern. So the general motto is be algebraic as long as you can. If there is one thing that you would like to take back from this talk, it's the importance of algebraic composition. Because algebraic verification is the cornerstone of verifying the invariance of your domain model. But everything cannot be done through algebra. We need to have, as I was saying, communication across bounded contexts. And for that we need to have reactive protocols. And we will be using asynchronous messaging for this. Message-driven, loose coupling, isolation, async message passing. We are now in this part of the graph, where we will discuss how you can make things responsive by being asynchronous message-driven. Quite some time back, Martin Thompson, one of the leaders in asynchronous computing, he tweeted this one. Messaging provides for a natural mapping place for types and decoupling in space and time. For those entities which are decoupled in space and time, messaging gives you a very good substrate for implementation. One more tweet. Messaging is the best way to communicate between bounded contexts, but requires protocol design. This is the most important part. You cannot have arbitrary messages flowing across bounded contexts. You need to have a protocol. And that's also explicitly explained in Eric Evans's excellent book on domain-driven design, where he discusses bounded contexts. He discusses a bunch of ways in which you can communicate across bounded contexts. One of them is the conformist mode. Here we have two bounded contexts, account management and reporting and analytics. They are completely decoupled in time. Account management is possibly an online system, whereas reporting possibly runs once a day or twice a day or thrice a day, something like that. So you cannot make a synchronous call from account management and expect some response from the reporting bounded context. You need to have a protocol, you need to have a message protocol between these two bounded contexts. It can be a pub sub. Push account information as messages downstream and it will consume according to its need. And the conformist thing means that account management is the master bounded context. It decides what the protocol should be and reporting has to conform. There are a bunch of other ways to collaborate as well. Okay. Now that we have seen how we can design static APIs that are algebraically sound or implement reactive protocols with async messaging that cuts across bounded contexts, you must be wondering why we haven't yet discussed actors. It's slide number 96, so better we start discussing some of the things that actors does in our domain model. And if you would ask me where I can use actors in a domain model, my response will be everywhere. I have seen this tendency to design an entire domain model based on actors. That's the problem, I think. Actors are powerful, too powerful, unalgebraically powerful. Of course, I'm excluding typed actors of Akka, which has been released only very recently. I haven't gone through that. So this is based on a pre-2.4 version of Akka. You gain power at one semantic level, but you lose the power of reasoning. If you have a static type system, why not use it to the maximum? I am not saying that actors do not have their uses. They have their uses, as we will see. But this is the problem. Using actors indiscriminately throughout your domain model makes algebraic reasoning hard. That's because futures have an algebra. You can fork a future, you can put something in, lift something into in the context of a future. You can do a map over future, you can join over future. Future is a monad. But for actor, it's something like this. So you can do almost anything with an actor. So the general principle, the general motto is use the least powerful abstraction that does the job. This is not only valid for users, futures and actors, it's valid for almost every aspect of software engineering. For example, applicatives and monads. Applicatives are less powerful. Use applicatives whenever you can. Use monads only as a fallback. And for domain model resilience, choose futures over actors whenever you can. Verifiability. For verifiability of your domain model, use futures over actors. In my experience of implementing domain models over the last couple of years, these are the two places where I found actors very useful. The first one is as an implementation artifact to protect shared mutable state. That's convenient, because or else in order to achieve this, I would have to use locks and threads, which obviously is a much lower level of abstraction and is fraught with grave perils. So actors provide a higher level of abstraction to deal with this concern, to deal with the fact that I can protect some mutable state. Mutable states are common in domain models. You cannot design a domain model without any mutable state. And if you need to protect a mutable state, you can use actors for that, but as an implementation artifact. Don't expose that as a public API. And the second one is, as Jonas was mentioning in his talk, centralized failure management, supervision hierarchies. Now, this is an example of an actor which is part of an implementation of a real life domain model. Transactions come and somewhere we need to aggregate them as the combined balance, per account balance, compute per account balance as part of an in-memory domain model. And the most performance efficient way of doing it is to use a mutable map. So we are doing that, we are using an actor in order to do that, and it's part of the implementation. And the other area where actors shine is centralized failure management. Jonas was talking about this error kernel. Designing your domain model around an error kernel is of invaluable help. It gives you the ability to track failures. It prevents littering your entire code base with try-catch blocks. And even you can with Akka you can have these supervision hierarchies to some extent declarative as well. So no more messy failure handling code scattered throughout. Your code becomes, your business logic becomes much cleaner. And you have a clean supervision hierarchy of how you would like to escalate your failures through the layer of actors. But it requires careful upfront design. You need to have your actor supervision hierarchy in place upfront. You cannot do it as an afterthought because your entire system design depends on that. Centralized failure management through actor-based supervision ensures that you don't have brittle failure management code littered across your code base. The entire management here is centralized, disciplined, and it also can be declarative if you use Akka. One other thing which I find quite common today is designing workflows, designing domain workflows using actors and messages. It works. There are lots of implementations that work this way, particularly if you use the higher level abstractions of Akka FSM, finite state machine, which it offers. But still, it's low level, untyped, non-compositional because actors don't compose, un-algebraic. And on the other hand, we would like to have something which is higher level, which is typed, which is algebraic, and which is compositional. Plus, it's good if we can have a DSL around it, a domain-specific language. Plus, since we are modeling workflows, we would like to have flow as a first-class abstraction. And this is one of the core principles of functional programming as well. Separate definition from execution. Because if you can separate definition from execution, you can compose multiple definitions to form a larger definition. So our wish list is this. We would not like to use the lower level actor framework for modeling our workflows. And this is exactly what reactive streams offer. Reactive streams offer a compositional type-safe way to model your stream-based workflows. And one of the implementations of reactive streams is Akka streams. It gives us natural abstractions for each of these artifacts. A source, computation starts from, the pipeline starts from a source, ends at a sink. Note this abstraction flow, it's a first class abstraction. And using flow, using flow source sink, you can generate a runnable graph, a graph of computation, which actually is the reified version of your workflow, domain workflow. You can compose multiple runnable graphs to form larger ones. You can reuse them, you can reify them. And finally, you can execute them. Now, this is an example of a business use case of a stream-based workflow where transactions flow from upstream to downstream, and at the end of the pipeline, we have some netting operations. And in between, we have a number of transformers that does lot of transformations depending on the workflow, what type of account it is, what type of transaction it is. Depending on that, it gives you a number of transformers. And if you translate it verbatim to Akka streams, you will see that the diagram also looks very much the similar one. You have the sources, you have the sinks there, and in between you have a web of transformations. And there, those transformers, they all encode business logic. They are all first class abstractions, they are all type safe. You can compose each of them. I will show you the code for this. The code for this also looks very good. And this is the code for this. For each of the artifacts, you define typed abstractions and compose them at the end. And this is the DSL. This is the DSL for composing the entire pipeline, which is declarative, which is type safe, which is compositional. And as I was mentioning, Akka streams use actors underneath to materialize this flow. So that's the main part of this implementation, that the actor part is delegated to the implementation level. The actor doesn't appear anywhere here. The public API doesn't have to deal with actor sends and actor receives. The public API is completely type safe, transformational, compositional, algebraic, all the good things are here. And this only creates the graph. It doesn't run the graph. As I was telling you, separate definition from execution. This only creates the graph. And once you have the graph, it's just a graph.run. Graph.run will, and you can compose multiple such graphs to build larger graphs. And at the end of it, you can say graph.run, which will run the entire stream processing pipeline. So if you have been using actors for modeling stream-based workflows, you can think of moving to Akka streams. It's one of the best things out there as part of the Akka stack. And one more thing which Akka streams handles is back pressure. One of the problems that we often find with stream-based workflows, when you have a pub and a sub, the subscriber often tends to get overloaded by flow coming from upstream. Akka streams has this ability. It gives you the hooks to control this back pressure by controlling the demand that the subscriber can actually tolerate. So all in all, it gives you a great substrate for composing stream-based workflows. Actually, there are a lot of other things as far as domain modeling with functional and reactive principles is concerned, but I don't have time for all of them. And one of the things is communication with the database. You can use event sourcing and CQRS, those kinds of techniques in order to communicate with the database, and Akka also gives persistent actors using which you can do that. But that's possibly a topic for a separate talk. So this is more or less what I have to say. And if you are more interested in this topic, I have written a book. It's actually coming up. The MIAP is early access is available from Manning. So, and don't forget to